In 1912, German meteorologist Alfred Wegener proposed that continents were once joined in a supercontinent called Pangaea. This idea, known as continental drift, suggested continents drifted apart over millions of years. Initially, Wegener's theory faced skepticism and hostility from the scientific community. Despite opposition, Wegener built a compelling case with evidence from various scientific disciplines. He noted the jigsaw puzzle fit of continents, especially South America and Africa. Identical fossil species found on now separated continents supported his theory. Geological similarities like the Appalachian and Caledonian Mountains suggested these landmasses were once connected. Paleoclimatology evidence, such as glacial deposits near the equator, indicated continents had moved. These clues collectively supported the idea of continental drift. Wegener's theory began to gain traction as more evidence emerged. The scientific community started to reconsider its stance on a static Earth. Wegener's theory faced rejection due to the lack of a plausible mechanism for continental movement. He suggested continents plowed through the ocean floor, but this analogy was flawed. Physicists argued that frictional forces would prevent such movement. Wegener couldn't explain the driving force behind continental drift. His status as a meteorologist, not a geologist, led to his ideas being dismissed. Established geologists were reluctant to accept a revolutionary concept from an outsider. Despite these challenges, Wegener remained steadfast in his convictions. His perseverance laid the groundwork for future discoveries. The scientific community eventually began to recognize the validity of his ideas. Advances in sonar technology during WITU revealed the ocean floor's secrets. Scientists discovered mid-ocean ridges, continuous mountain ranges encircling the globe. These ridges were sites of new oceanic crust formation. Deep trenches marked zones where the ocean floor was subducted back into the Earth's interior. This dynamic ocean floor provided a mechanism for continental movement. The realization that the ocean floor was active, not static, was crucial. It explained how continents could move without plowing through the solid ocean floor. The continents were carried along with the ocean floor like passengers on a conveyor belt. This discovery vindicated Wegener's theory and revolutionized our understanding of the Earth. Paleomagnetism provided crucial evidence for continental drift. Rocks preserve a record of the Earth's magnetic field at the time of their formation. Scientists discovered that ancient rocks' magnetic poles didn't align with the current magnetic field. The apparent wander of magnetic poles could be explained by continental movement. Fixed continents would imply erratic shifts in the Earth's magnetic field, which was implausible. Moving continents carrying magnetized rocks provided a coherent explanation. This evidence, combined with oceanographic discoveries, revived Wegener's theory. The scientific community began to accept the idea of a dynamic Earth. By the mid-20th century, evidence for continental drift was overwhelming. Discoveries from oceanography and paleomagnetism forced a paradigm shift. The emerging picture was of a dynamic Earth with moving continents. Plate tectonics theory explained the movement of continents on massive interlocking plates. These plates interact at their boundaries, causing geological phenomena. Seafloor spreading at mid-ocean ridges drives continental drift. Plate tectonics provided a unifying framework for understanding Earth's geology. Plate boundaries explain earthquakes and volcanoes. At convergent boundaries, plates collide, causing subduction and volcanic activity. Oceanic-continental collisions form volcanic mountain ranges like the Andes. Continental collisions create towering mountain ranges like the Himalayas. Plate tectonics explains the distribution of continents and oceans. It also accounts for the occurrence of earthquakes and volcanoes. These events are consequences of interactions between Earth's moving plates. Plate tectonics revolutionized our understanding of geological processes. Plate tectonics shifted our view of Earth from static to dynamic. Continents are in constant motion, shaping the planet's surface. This movement influences climate, ocean currents, and life evolution. The interconnectedness of geological processes became evident. Plate tectonics is a cornerstone of modern geology, explaining Earth's past and future. Alfred Wegener's theory faced ridicule but ultimately triumphed. His perseverance and willingness to challenge orthodoxy paved the way for a revolution. Wegener's legacy inspires scientists to think outside the box and follow evidence. The acceptance of continental drift stands as a triumph of scientific progress. Wegener's story reminds us that radical ideas can reshape our understanding of the world. Plate tectonics has implications beyond Earth. Other planets and moons may also experience tectonic activity. Plate tectonics plays a crucial role in maintaining Earth's habitability. The search for life on exoplanets considers tectonic activity as an indicator of habitability. Active geology suggests potential for life-supporting conditions. Lessons from Earth's geology guide the search for extraterrestrial life. Wegener's story is a testament to human curiosity and the quest for understanding. Plate tectonics filled us with wonder and reshaped our view of Earth. It influenced our culture and inspired art, literature, and music. Wegener's legacy encourages us to ask big questions and explore the universe. The triumph of his theory continues to inspire scientific exploration and discovery. And as always, if you appreciate Earth's history and learning new things, give the video and channel what you think it deserves.